not all electric discharges are quite as dramatic as those lightning strikes, but if the gap to be crossed is narrow enough, the build-up of even a relatively small amount of charge can cause the sparks to fly. So, how does a charge build up like that in one place? Well, it's carried there by vast numbers of microscopic charged particles, usually ions or electrons. The electron carries the smallest charge known to exist in nature. Every atom in every substance contains at least one electron. But electrons are so small that nobody's actually ever seen one. However, there are lots of experiments you can do to demonstrate indirectly the existence of electrons and to measure their properties. And in this program, we'll show you a selection of these experiments, like this. If we're going to investigate the properties of electrons, first of all we need to know how to produce them, or at least free them from their atoms. And then we need some means of observing them. Remember, electrons are too small to see directly, so we have to detect them by the effects they can generate. This glowing spot is the result of a beam of electrons striking a luminescent coating. It's much the same process as goes on inside your television, in fact. If you actually wanted to collect the electrons, you could do so with this device here. So, how are the electrons produced in this tube? Well, at this end, there's a wire filament that's electrically heated. You can see it's glowing. Electrons are ejected from the hot wire and emerge through this small hole as a beam. Now, if the tube were full of air, the beam wouldn't get very far, because in colliding with air molecules, the electrons would get knocked off course. So this bulb is evacuated. With relatively few air molecules to deflect it, the beam travels right across the bulb until it gets to the luminescent screen. It rather looks from this as though the beam travels in a straight line, and we can check that over here. Now, you know that light travels in straight lines, and if we lower the overhead lights, then this cross casts a sharply defined shadow. Now, instead of shining a beam of light on the cross, I'll shine a beam of electrons. We can't actually see the path of the electron beam, but we can see what happens when it hits the luminescent screen. Again, a nice sharp shadow. So this arrangement confirms that electrons, like photons of light, travel in straight lines. But there are various ways of deflecting electrons from their straight paths, and the next experiment will let me demonstrate one method of doing this. In this tube, the electrons are directed not through a hole, but a horizontal slit. So the beam is a flat one, like a ribbon in this plane. And the luminescent screen is also flat, and it's set at an angle to the beam. Seen in section, the far edge of the beam strikes the right-hand side of the screen, and the near edge of the beam strikes the left-hand side. Now, here and here are metal plates connected to a high voltage supply, so that a voltage difference, a potential difference, can be established between them. So, let me do that. This side of the beam isn't influenced by the plates, but by the time the beam has travelled to this side, it's been deflected by the potential difference. Now, the way the plates are connected at the moment, this one is negative with respect to this one. If I swap the connections, plus to minus, the beam is deflected the opposite way. So, whichever way the potential difference is set up, the electrons are always deflected away from the negative plate towards the positive one. experimental proof that electrons are indeed negatively charged and are therefore repelled by other negative charges, attracted to positive charges. So, electrons have a negative charge, but is there any evidence that they have a particular amount of charge?
One of the nicest pieces of information that we have comes from an experiment which was performed in 1909 by the physicist Robert Millikan. It's a very simple but clever little experiment, and he won a Nobel Prize for it. It was obvious to him that electrons were much too small to be seen. So instead of looking at the electrons themselves, he used small drops of oil. He produced a fine spray. And in the spray, the little drops get charged. In his experiment, Millikan put his oil drops between two plates, metal plates on which he was able to place electric charge. So let's see what happens if we put a charged drop between two charged plates. Now, to see the drops, we need some light. And I've got a television camera pointing in between the plates. Normally, I'd be looking at this with a microscope, but you want to see the drops too, so that's why I'm using a television camera and a big weight on top to hold it steady. The rest of the apparatus is a power supply to put an electric potential between the two plates, a switch, and in the top plate, there's a small hole to get the drops in. Now, to prevent drafts, I have a chimney and a small device for closing the hole. Right, we're ready. The spray, open the hole, and close it. Now watch what happens when I increase the potential. I'll switch it on now. Notice some of the drops are moving up. They're being attracted up towards the top plate. The force up is bigger than the force down. First, I'll pick out a suitable drop. That's provided by increasing and decreasing the voltage to get rid of all the other drops. Well, now I've selected one drop, and I'm going to adjust the voltage to keep it stationary. Increasing it now. Decreasing. And that seems to be about stationary now. Okay. So there's a downward force due to gravity, and there's an upward force, which is an electric force, because I've charged the plates. I want to keep that drop and change its charge. What I'm going to do is bombard it with electrons. It's already got a positive charge, and if I fire electrons at it, then it'll pick up electrons, and the charge will change. So to do that, I'm going to use a source of beta rays, which are just electrons. The dreaded strontium-90, an isotope of strontium that emits beta rays. And we put it in a little holder which points between the plates. There. When I open a little gate here, the beta rays will pass between the plates. Hopefully, some of them will hit the drop. But first, I have to switch off the potential. Otherwise, all the beta rays will be attracted towards one of the plates. When I switch off, the drop is going to start falling. So what I want to do is just get the drop up to the top of the screen so it's got plenty of room to fall in. Here we go. There, that's holding the drop fairly steady at the top of the screen. And now we switch off the potential and open the gate. Let's hope it's collected an electron this time. Getting near the bottom, so gate closed, potential on. It's still dropping, so I'll increase the potential. Get it up near the middle now. We'll find what voltage we need to keep it steady. Well, that seems to be about it. Slight touch down, perhaps. Yes, I'd say that was steady. About 520 volts.
You've seen Charlie get two values of the voltage needed to balance the oil drop. He produced an electrostatic force in the upward direction, just enough to balance the downward gravitational force on the drop. Now, it's rather a fiddly experiment to do, and Charlie spent a lot of time getting some more voltage readings. You'll find those in the text. And what we'd like you to do with them is to see whether they're all consistent with the idea that the charge on the oil drop is just some whole number times a smallest possible charge. In fact, the charge on the electron. Now, Millikan went a bit further than that. He actually measured the charge, and he found it to be about 1.6 times 10 to the minus 19 coulombs. I've been talking about the electron as a charged particle. If it really is a particle, then it must have mass, and we should be able to show that. One of the most convincing demonstrations involves an arrangement like this. If I strike this vane, it oscillates. Now, in the actual experiment, which is recorded on a rather old piece of film, the vane is struck by a beam of electrons. When the accelerating potential is applied, the electrons flow along the middle of the tube and strike the vane. In fact, here the suspension's so fine that even when no electrons flow, the vane shudders rather because of vibrations in the room. Now the electron beam is switched on and off repeatedly, and the green patch glows each time a pulse of electrons strikes the vane. At first, the oscillations are small, but you see, if I strike this vane repeatedly at the same frequency as its natural oscillation frequency, we see that the amplitude of the motion builds up. Similarly, by now, repeated pulses of electrons at just the right frequency have caused the oscillation to build up. Now, at every collision of an electron with the vane, momentum is conserved. With each pulse of electrons, the magnitude of the vane's momentum increases. So, the incoming electrons must possess momentum, and this indicates that they must also have mass. Obviously, the next step is to try to measure that mass, and to do that, we can make use of another property of charged particles, the fact that in a magnetic field, they're deflected from their normally straight paths. I can demonstrate this with the tube I had earlier on. Here's a beam going straight through, because there's no external influence. Now watch what happens as I bring up one end of this bar magnet. And if I reverse the magnet, And again. Incidentally, don't try this kind of experiment on the tube of your TV set, because it might damage the colour screen. Now, bar magnets are all very well, but the field they produce is rather weak, and it's difficult to measure. So, for quantitative experiments, there's a much better way to produce a magnetic field, as you know, using a coil. At the moment, there's no current going through this coil, so that this direction indicated by the compass needle is north-south. Now, if I turn on the current, the compass needle is deflected. The current going through the coil has generated a magnetic field here. Turn the current down, it moves back to its original place, turn it up, and it's deflected again. And if I increase the current, the deflection also increases. So, the greater the current, the greater the magnetic field strength. Now, the details don't particularly matter, but it is in fact possible to calculate the magnetic field strength at any point, just knowing the size of the coil and the amount of current flowing through it. And it further turns out that the most uniform magnetic field is produced not with one coil, but with two, arranged like this, so that their separation is equal to their radius. So, let's try the twin coil arrangement with the electron beam. Turn up the current through the coils, and the beam's deflected. Now, if I reverse the current through the coils, turn it up again, and the beam moves the opposite way. If we're going to make this experiment quantitative, we need to decide what the deflection depends on. Well, neutral particles aren't deflected by magnetic fields, so clearly the deflection depends on the charge, and it also depends on the mass of the particles. I can show that on this model. This steel ball represents an electron accelerating through the tube. A magnetic field here deflects it from its straight path by this amount. If I use a more massive steel ball, the deflection's much smaller. In fact, the deflection is inversely proportional to the mass of the particle. So, just to recap on that, the deflection's directly proportional to the charge on the particle and inversely proportional to its mass. In other words, what we can get out of this kind of experiment is not the charge or the mass separately, but their ratio, the charge to mass ratio. This ratio was first measured in 1897 by J.J. Thomson, but to do it, he had to find a way of measuring one other quantity, the velocity of the electrons when they enter the magnetic field. You see, slow-moving particles are deflected more than fast-moving ones of the same mass. Going back to the electron beam, we can find the velocity by combining the magnetic and electric effects. Let's start with the potential difference across the plates which deflects the beam. Now, I've set this up so that I can balance the electric deflection with the magnetic one, like this. So in effect, what I've done is to balance the electric force on the electrons by an equal, but opposite, magnetic force. Knowing the strength of the magnetic field and the potential difference between the plates, Thomson was actually able to calculate the velocity of the electrons in the beam, and hence their charge to mass ratio. And the value he got was 1.8 times 10 to the 11 coulombs per kilogram. I'll leave you to work out the mass from that. Now, we're not restricted to studying electrons in this kind of experiment because any beam of charged particles will be deflected in a magnetic field. So, in principle, we can determine the charge-to-mass ratio for any particles. Suppose that instead of negative electrons, we used a beam of positive ions. In our analogy, we can represent a mixture of ions of different mass by these balls. But we'll suppose that they all have the same charge because they're all a result of an atom having lost one electron. Right, now we accelerate them, in this case gravitationally, so that each ball has the same acceleration. And you can see the magnetic field sorts the ions according to their mass. If we can arrange to detect these ions, we've got a means of measuring the charge-to-mass ratios of each ion in the mixture. And we already know the charge. It's equal and opposite to the charge of the one electron that each atom lost when it formed its ion. So the experiment enables us to measure the masses of ions. And these are so much more massive than electrons that in effect what we're measuring is the masses of atoms. The actual device for doing this is called a mass spectrometer.
To record a mass spectrum, we've come to University College, where Dr. Alec Loudon is going to produce the mass spectrum for us. He's already filled the bulb with neon gas. Come and have a look at how the ions are separated in the mass spectrometer. We've got a lot of electronics, and to get rid of the air, we have to use some big pumps. But the interesting parts of the instrument are the ion source, where the ions are produced, and the ion collector down here. Connecting these two is a curved path, where the ions are separated into different masses. To separate them, we need a magnetic field. So let's get the magnet in. It weighs a little over a ton. There. Well, now we should have a spectrum. We've got 3 peaks. How do we explain that? Well, neon consists of 3 different kinds of atoms, 3 different masses. Now, we call atoms of an element which have different masses isotopes. So neon consists of 3, neon 22, neon 21, and neon 20.
An atom of neon is 2 to 3 times less massive than an atom of iron, and that has a mass of about 10 to the minus 28 kilograms, which tells me that there are about 10 to the 22 atoms in this ball.